Okay. Now, before we proceed further, I need to refresh your memory in terms of the transmultiplexer. A transmultiplexer is one that generates a frequency division multiplex signal, generates a frequency division multiplexed, that means typically a wideband signal, wideband signal. Now, practical transmultiplexers, this is what they would do. So, if I were to give a set of 3 signals, one of them of this type, a second signal which is same bandwidth but different spectrum, and a third signal which has something different, again bandwidth. So, the practical transmultiplexer, the transmultiplexer that takes these signals, so these signals coming in to a transmultiplexer, practical transmultiplexer will generate for me a signal that looks like this. Okay. Again, these are conceptual. So, there would be the blue signal, the green signal, and then the red signal. Okay. Key question, why were there gaps? It is a practical transmultiplexer. So, I need to be able to filter out and recover the signals. So, the only way I can do that is if I can have a filter that is flat and then has got some roll off, and so that it does not distort my signal, but again at the so this gap is actually inevitable. We call it the guard band. The guard band is one that helps us apply practical filters. So, we said that we are talking about a practical transmultiplexer. These are guard bands. Guard bands are wasted spectrum because that is not useful. So, therefore, it reduces the overall efficiency of your transmission scheme, but you cannot avoid it because that is part of the. Now, on the other hand, we saw another transmultiplexer, this is the practical transmultiplexer. We saw another, there is a multi-rate concept called transmultiplexing, where we did the synthesis filter bank, and there we said, well, I am just going to upsample and I am going to create the following multiplex signal. It is going to look like this. Why? Because I did not use any excess bandwidth. Okay, dot 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 on both sides. That is a transmultiplexer that does not have guard bands. Okay. But again, we did not yet gone into the process of actually designing these filters. So, it is very important that we sort of retune ourselves, saying yes, there are some practical constraints, but at the same time my multi-rate concept says if I have 3 channels which have got bandwidth B, I should not be using more than 3B. That is the only way I am maintaining the optimality of the signal. Okay. So, this is one concept I just want you to keep in mind, and another related concept that is also important. So, today what we are doing for water filling is this, am I right? You are dividing the channel into subbands, or your signal into subbands, and you are assuming that the signals are orthogonal, but what will it be in practice? In practice, there is going to be some amount of roll off. So, which means that there will be overlap between subchannels. Okay. So, this is going to be the practical case. This is the practical case, this is the ideal case. Now, we know that we can achieve even if the 2 waveforms are overlapping in frequency, there are certain conditions that you can impose on them to maintain orthogonality. So, therefore, we can generate orthogonality, but this is very important. So, a way to think of the OFDM, okay, OFDM is, first of all, it is some form of transmultiplexing. Right, it is some form of transmultiplexing. Then you have to maintain orthogonality. And you want to achieve with practical filters. you want to achieve with practical filters. That is also a very important consideration. So, a transmultiplexer that maintains orthogonality, that has practical filters, and a very important one, optimal bandwidth. Okay. Now, what you are saying is, hey, I have to maintain orthogonality, which means there is going to be overlap, and in the process do not give me guard bands, I do not want to waste time in guard bands, and if I can achieve all of this, then we are talking about OFDM. Now, you see why OFDM is of so much of interest. For the following reason, I can achieve capacity, I can achieve any wasted, I can achieve with the practical filters, I can achieve it. I can achieve it without asking for too much of excess bandwidth. So, again OFDM becomes a very interesting issue for us. However, one catch is there. What about equalization? Yeah, you kind of said, all wideband, everything. Now all of a sudden you kind of didn't really address the equalization issue. No, we actually have addressed it. Actually, yesterday's this is a recap. So this slide is just reuse from yesterday's talk. So yeah, we said that typically in a practical channel, this 5 microseconds is actually a very practical number. Many measured wireless channels have got RMS delay spread roughly of the order of 5 milliseconds. Okay, so that is why we are using that number. And if I use a 10 megahertz signal, that means my baud rate is approximately at 10 million, which means my symbol rate is 100 nanoseconds. Came out to be 50 symbols of ISI. That means the transmitted symbol now may show up after 50 symbols have gone by. So, which means that at any given time I have overlap of 50 symbols, which means ISI of 50 symbols, which means the complexity is going to be 16 power 50. Okay. Here comes the most important element. Now, the previous case, what was the bandwidth? 10 megahertz. Okay. Now, ask the question, supposing my bandwidth had been 10 kilohertz instead of 10 megahertz, what would be the symbol duration? What would be the symbol duration? It would be 1 over, the baud rate would be approximately 10,000. So, symbol duration would be 1 over 10,000. Okay. So, approximately you are talking about something in the vicinity of 100 microseconds. 100 microseconds. Sketch it for me. What does this look like? Okay. So, here is a symbol. Here is a symbol that is 100 microseconds long. Okay. Okay, 100 microseconds. This is 100 microseconds. An echo is coming with a delay of 5 microseconds. Okay, here is the echo. That is it. So, what does it look like to the signal? Well, some small disturbance is there, but it is not from something which is 100 symbols away, it is my own symbol which is just delayed. So, how much inter-symbol interference will you get? So, the previous symbol, let us say was transmitted as purple, you will get some amount of combination from the previous symbol, that is your inter-symbol, very small. So, this is a case where ISI would be more or less can be ignored, you can treat it like noise and say, well, it is some small impairment, I am just going to treat it like noise. And as we mentioned yesterday, the RMS delay spread, if your RMS delay spread sigma tau is less than 1/10 of your symbol duration, right, 1 or 0.1 times the symbol duration, then you can more or less say that my channel is considered flat. So, this is a case where you could almost treat it as a flat channel. So, this particular scenario would be a flat channel. Now, notice that this 5 microsecond RMS delay spread actually looked like a terribly dispersive channel for a 10 megahertz signal, but for a 10 kilohertz signal it was not a problem at all. So, the goal is choose your n number of subchannels such that you get 10 into 10 power 6 divided by 10 power 4, which basically means that roughly of the order of 1000. You divide your bandwidth into 1000, then all of a sudden your time dispersion becomes non-issue, your ability to achieve capacity becomes all of a sudden, you could, working with a 10 megahertz channel, it was very difficult to do equalization, no possibility of doing achieving channel capacity, and now all of a sudden you are saying, hey, I now have the ability. So what we have done is you took a wideband signal 10 megahertz, you divided it into sub channels, each of these sub channels were 10 kilohertz wide. So this was 10 kilohertz, and then you completely transformed the problem into a domain for which we have a lot of tools. Okay, so this is why we are so interested in OFDM. This is why, see, otherwise from a multirate point of view, it's very easy to introduce OFDM. Just take the DFT, that's it. But why are you interested? Why is it so important for us to study OFDM in this context? Now, supposing this were the case, how would you do the equalization? Okay, so you can almost ignore equalizer, but if there is some dispersion, how would you do the equalizer? Another very important question for you to answer me. So in other words, I have achieved the following. Okay, I have divided my broadband signal, wideband signal into subchannels, and these subchannels, some of them are seeing good channel gains, some are not seeing very good channel gains. Okay, so this is the scenario that I am seeing. Now this is the channel gains. Okay, so let me write it down here. So what we have shown here is channel gain after I have divided into subchannels, channel gain, and this is frequency on this axis. Okay. Now as long as the channel gain is not flat across the various entire bandwidth of the signal, that means I do have frequency selective fading. That means I must do equalization. How do I do equalization for an OFDM or this multi-carrier type of signal? Very easy. We say that, okay, pick some reference point, okay, and whatever is the distance between that, you just boost it up, just boost that sub channel up. Okay. So typically what is the reference line? I take the reference line as 1. That means by how much should I boost? If this level is h naught of j omega magnitude, if that is the level of the first channel, then I must boost this by 1 divided by h naught of j omega. Okay, that will bring me up in terms of magnitude and phase. So actually you do not need to use the magnitude, let us use the actual. So if that level, it is a complex number, if I do 1 over h naught. So for the second one, what should I do? I will do 1 over h1 of j omega. So you just take the frequency response and take the reciprocal of it, all those channels will get boosted up and you will see a flat line. Okay. Now is this water filling? I see yes and no. Which way is it? No, this is not power. So what am I doing here? I am equalizing, I am sort of balancing the channel gain. So it looks like water filling, don't mistake it for water filling. So this is not water filling, this is not water filling. What is it? It is actually equalization. It has another name, you probably have always thought of equalization in terms of time domain. This is actually frequency domain equalization. So this is called FDE. So when we say that these multi-carrier signals like OFDM have very simple equalization, what do we mean? Calculate the channel gain, take the reciprocal of the channel gain for those channels, then we are through, we get the. So when we say very simple equalizer, a frequency domain equalizer just requires you to compute 1 over hj, or let me use some other, I do not want to use this, hk of j omega, k equal to 0 to n minus 1. Okay. There are n sub channels, I am going to equalize them in this fashion, and this is also, it is referred to as a single tap FDE, because each channel gets only one tap, right. There is no, you do not have to have a filter, single tap FDE. So, this is the beauty of OFDM, or the system that we are studying, and that is why it is so important for us from a communications perspective. It helped me achieve capacity, it solved to some extent the equalizer complexity problem. So, now let us see what are the key elements of this concept, how do we take it forward, and how do we exploit it to the maximum possible. So, the material that we are going to be now studying is actually found in Goldsmith chapter 12, would definitely encourage you to read that. Okay, it is under the heading multi-carrier modulation, not necessarily did not call it as OFDM, but we are going to develop it into a OFDM chapter, okay, multi-carrier modulation, MCM. Okay. So, if you go and open Goldsmith chapter 12, here is what you are going to see, the first statement. Okay. The first statement is that divide your transmission bandwidth. This is the first statement that you will see, and I hope you will go and read that, into subchannels, okay. And you know why, you are dividing into subchannels, no problem, okay, that is well understood. Okay. The second statement that you will find is that these subchannels bandwidth are chosen such that they are much less than coherence bandwidth. And you know why? Because you want the frequency gain to be constant. So, the statement will be that if you choose it according to this, you will have approximately flat fading. I know exactly why this statement is there, and because you already know the background of what has already been discussed here. So, basically this will be a scenario where you will have approximately flat fading. Okay. This also says that it is equalization is simple. Okay. Why? Because you know that you can do a single tap frequency domain equalizer. So, either you can avoid equalizer, that means you will have some residual ISI to contend with, or you can have a simple one tap FDE. Okay, both of which are very useful for us to understand. Okay. Now, there is a block diagram that will be given in Goldsmith's book, and this is what the block diagram is. Of course, if you saw this first, you may not have necessarily linked it to the other concepts that we have talked about, but otherwise this is what you will find. So, the block diagram for multi-carrier modulation is the following, where I have a channel or a data source which is coming at r bits per second. I am going to do a parallel to a serial to parallel converter. I will come up with n parallel channels, each of which is containing r over n BPS. So, this is channel number 0, channel number n minus 1. Okay. Now, each of these channels, let us quickly trace what the path of them is going to be. You will group them in these bits into either 2 bits or 3 bits sets, and then map it onto a symbol. So, the first stage will be a symbol mapper. You will take the bits and then you will map it to either a QPSK, 16 QAM, 64 QAM, whatever you want. Then the next stage is you have to prepare it for transmission. You will do pulse shaping. Pulse shaping is to ensure that you have a compact bandwidth. So, pulse shaping, okay, raised cosine, any of those types of pulse shaping is permitted, that is done. Now, you have to translate it into carrier frequency. Okay. So, the multi-carrier modulation says first channel I am going to translate it to a frequency f0, 2 pi f0 into t, okay, and then add it up. The second branch, branch number 1, would go through a symbol mapper. So, this is number 1, symbol mapper will go through a pulse shaper and then will come out, and then you would have a second carrier which would be cosine 2 pi f1 into t, 2 pi f1 t, that is my second carrier, and then the last one will be cosine 2 pi f n minus 1 into t, that will dot dot dot. So, basically you have got all of those, and this and modulated to different center frequencies. So, this is the notion where you are trying to generate something of this type. Okay. This is at a center frequency f naught, the second one is at a center frequency f1, and the last one is at a center frequency fn minus 1. So, this is what we are trying to generate. Okay. It is an FDM signal where these frequencies are chosen so that orthogonality can be preserved. This was how multi-carrier modulation was envisioned. Okay. This is now again this has no reference to the multirate parts, it does not have anything to do with transmultiplexer, but just say this is how I want to transmit these signals. Now, the question is, who were the first one to come up with this concept and why? The first people to come up with this concept was military. Okay. Why would they want to do this type of a transmission? Why would they want to do this type of a transmission? Okay. First thing, supposing I did not have to use all these frequency bands, okay, my data is sufficient that it will go on one of these bands. So, at any given time I will keep changing my center frequency, you cannot jam my signal, understood, number 1. So, because it looks like my signal is suddenly at f naught, you try to jam there, I would have already have moved to this one. So, this is a very attractive scheme for that. The other one is you can scramble your signals, right. You can let us say so if I was interested in tapping one of these signals are constantly getting scrambled. So, signal number 0 goes on this carrier for some time, it goes on this carrier and then switches. So, basically your information, so you are transmitting on multiple channels, but the data is getting mixed up. So, at the receiver, if you try to even if you manage to decode the bits, you do not know how to put them together, because only you know at the transmitter how you have scrambled the signals across. So, the military had several reasons for doing it, and of course, they would have to do a practical transmultiplexer. So, they would have these frequency bands. Then of course, over a period of time there was another development that happened, and let me just show you one slide and then we will stop with that. Okay. So, here is a slide which says this is how multi-carrier modulation evolved over time. Military used it in the early 50s. Very early in 1966 they saw commercial potential for this, and it was a telephone company called Bell Telephone System. Okay. Now, why did they see value in this particular system? And in fact, if you can see all the development all the way from 1960s all the way to 2000, almost 40 years, it all came from people who are using either telephone or television cable for transmission. And let me end with that statement as to why they were interested and why they. So, the scenario for a telephone line was this. This is the channel gain magnitude, okay, magnitude of the channel gain as a function of frequency. Okay. The telephone line had a response that looked something like this. It had reasonably flat response to around 4 kilohertz. and that is why all voice transmission happens in 0 to 4 kilohertz. Okay, it does not have very good transmission around DC, so you do not extend it all the way there. So it starts from low frequency all the way to 4 kilohertz, and after this it just sort of goes off. So what people did was, well, you know, the gain is falls off very fast, so basically at high frequencies there is really no use. So they always thought that the telephone line, by the way, this goes to probably several megahertz. Okay, so several megahertz, the response goes up to several megahertz, 2 megahertz, 3 megahertz. So the question is, basically you ignore the bandwidth between 4 kilohertz and 2 megahertz for that matter. Okay, because the portion that you are transmitting has got good gain, you forgot about. Then people said, hey, you know what, this bandwidth is actually quite big, can we use it for transmitting data? Okay, leave the 4 kilohertz for voice, this one. So this is where these modems came about, this digital subscriber loop modems. Digital subscriber loop was a telephone line, but they were used to transmit data. They left the 4 kilohertz, and then so DSL modems came because they recognized that the bandwidth of the channel was much larger. But the problem is, you transmit any signal through this, it will get very heavily distorted because your channel gain is, but the good thing is it is not changing, it is more or less somewhat constant, and you can so digital subscriber loop. So I say that, okay, leave this portion, I want to transmit something on this part. Okay, so if I transmit a signal that is like this, it is getting heavily distorted, and equalization becomes complex because I have to now design a very complex equalizer. Then these people said, hey, you know what, do not do this, transmit in small narrow bands. And then what do? Do water filling, do single tap equalization, get the signal out and get. So this is why they were interested in. So telephone cables, TV cables, all of them saw that, hey, there is a portion that is being used, and then there is a huge portion that is not being used, and the reason it is not being used is because it does not have a constant gain or a flat gain. But no problem, I know how to achieve capacity for those, and we can actually use that information. And today you can transmit several megabits of information, almost hundreds of megabits per second, on using this what was considered as wasted bandwidth of the telephone cable. So that's why the telephone people became interested, and that's why you see for almost 40 years of development was nothing to do with wireless at all. It was people who were trying to get the maximum out of the telephone channel, basically when there is non-uniform gain. And then the wireless people came and said, hey, you know what, that is useful for me as well, because I have a system where the channel gain is not constant, it is fluctuating, no problem, whatever technology you have developed, I can take it and then apply it. That became OFDM. We will pick it up from here in the next lecture. Thank you. By the way, tomorrow we will meet. Thank you.